This talk is about partitioning in Postgres, and the tagline is, of course, that simple things always work best. I worked in IT for over 20 years. I spend my spare time on a motorcycle. I'm a bit of a dino, so I went to Poland and took this picture of a dino supermarket. Here's your IT dinosaur. Customer list, if you're interested. What do? I mainly sit at the desk and drink coffee. This was my desk a while ago, to a lot of empty coffee cups and the earphones for the conference calls. This is what we do these days. So we talk about partitioning on this one. And why partitioning? Why this talk? Well, I've seen a number of interesting failures of people who wanted to apply partitioning. And then after attempting to apply partitioning, they come to the conclusion, maybe not. Let me help you prevent that sort of failure. And the summary, of course, is you need to put it in your design. Partitioning only works well if you do that from the start, when you design your system right up front. If you try to bolt on partitioning on a running system, 9 out of 10 cases you'll probably fail for various reasons. Have a look at the final slides. My top tip is always to keep it simple. So whatever you do in partitioning, make sure you can explain it to me. Keep it simple. After the talk, I hope there is a bit of time for discussion. I really missed the live events. There's a few things in this presentation, but I expect a lot of people to say, "Ooh, I would do that differently." And that's fine. I'd like to hear that, actually. So the basics, what and why of partitioning? Well, you already know, probably. Partitioning means you split one large table into many, hopefully smaller tables. You will do this for two main advantages. The first advantage is in manipulating the data, you generate less wall. You avoid generating a lot of write-ahead log. That makes your system more efficient. The second advantage is when you query your data, you hope to scan less partitions, you hope to scan less data, and your queries become faster. This is your second advantage. There is a lot more. You can use range, list, or hash partitioning. We can discuss that. You can put data in different table spaces. You can play with the location of your data for fast disk, a slow disk, old disk, colder, the hot and cold disks, that sort of thing. You can discuss with your system admin about storage tiers, quite interesting, but next PowerPoint, later. The tables and indexes, let's have a recap. We've got a table. In the table I've got records, and the records are all over. Record number 1 is not necessarily at position number 1, and record number 4 is not necessarily at the end of the table. That's why I've got the index in there. I can order my keys and I can use the index to look up number 1. So if you want to know where record number 1 is, I go to the index, I ask, point me to record number 1, and it points me to that record. Same thing, if I want to look for number 4, I look it up in the index and I go to 4 straight away. If I have a partition table, my data is more or less located in a partition. So first partition contains all the data starting with 1, third partition contains all the data starting with 3. And the indexes on those partitions are small, are local. Every partition has its own index. So the index for partition number 1 only points to partition number 1. It doesn't point to any records in the other partitions. It can't. The index on the second partition only points to the second partition, and so for 3 and 4. So what I have is, I have smaller pieces, and I have known content in each piece. I know that in partition number 2 are only the records for the range, or the set that belongs to partition number 2, and the index for partition number 2 can only point to records in partition number 2. For developers, applications, and queries, this is still one big table, and they can query with whatever where clause they like. And what is interesting here is to note that we've got local indexes. Every index only points to one partition. The notion of a global index, we'll come to that in a moment. So here's the first advantage. I'm generating less write-ahead log. When I do inserts, updates, and deletes, that is work, and I'm generating write-ahead log, and I get vacuum activity in Postgres if that's the case. My write-ahead log means I have local I/O. I may have to stream that to a replica system, meaning I also have remote I/O. I have work sort of perpetrating through my whole system. If I can reduce the write-ahead work, I make my system more efficient and therefore faster. The best example is always on a delete. You can delete the data, generate wall, but you can drop or truncate, and that is much faster. This is the efficient delete, just drop or truncate part of the table. And with partitions, you can, because you can drop the partition, or in Postgres, you can drop the table that represents the partition. However, that only works if your partitioning is suitable, meaning you drop a partition, you want to know that exactly the data you need to delete is in that partition. The same thing when you attach or detach tables to your partition table. They have to fit. This is where your design comes in. You have to know what data goes into what partition and when you want to manipulate or drop or exchange or attach and detach those partitions. This is your design. So how does it work? Well, you've got your partition table with the local indexes. So you want to delete something, you want to delete everything that starts with 1, you do the a drop table pt1, and poof, it's gone. It is that simple. And this is not a delete action followed by a lot of vacuum and a lot of wall effort. This is a dictionary effort. So it is as instantaneous as a click of a mouse almost. Rather than deleting 10,000 records and doing a lot of work, you say, just drop this table and it's gone. In a demo, of course, we'll create a conventional table, we'll create a partition table, we'll delete from the T and observe the wall, we'll delete from the partition table, and we still have a lot of wall going on. But if we then drop the partition, it becomes a lot more efficient. Let's have a look. That's the demo. Yeah. I'm initiating my demo. I'm creating a partition table. The key is an ID field, a big int. It's got a primary key on there, and the range is also on that ID field. So this is my primary key and it's my partition key. And this is the year 2020. I'm on version 12. I'm going to add the partitions to the table. So I've got my table pt1, partition for values 0 to 10,000. I've got my partition pt number 2 for values 10 to 20, pt number 3, pt number 4. So I'm attaching 4 partitions to my partition table. My partition table is now ready to receive data in the ranges from 0 to 40,000. To compare, I'm creating a conventional table T, same fields and a same primary key. I'll put in the same data in a bit. Inserting 40,000 rows, 40,000, just a counter as an ID, and I'm sneakily putting in a field called active, which has the yes or no values. I can put in a few yes values and a lot of no's just to demonstrate index lookups. Inserting into conventional table, inserting into partition table, create a few additional index just for good measure. The more indexes on a table, the more wall you will have on manipulating the data in the table. I just put in 2 big indexes to get a lot of wall when I delete stuff. You can look at the data dictionary and then you see that you've got your table, parent table pt1 has partition pt1, which is a partition relation to that table. The data dictionary in Postgres is fairly new to me, so I thought this was interesting. My demo is ready. I've got a conventional table, I've got a partition table, I have 40K records in each, and I've got 10K records in each partition. Let's demo. So what was the demo again? I will delete from T, I will 10,000 records. I will delete from the partition table, and then I'll show you a drop partition and how blightly efficient that can be. Deleting from table T, 10,000 rows, generates about 10 MB of wall. I'm deleting from my PT table, my partition table. You know and I know that all this data is in the first partition, but Postgres doesn't know that yet. It's generating 10 M of wall. Now let me drop a partition, and suddenly by dropping PT2, I'm effectively deleting another 10,000 rows from the table, and I generate 27K of wall. That's a lot less than the 10 M. See how much more efficient the drop of a partition is compared to the deletion of the data. This was the whole demo. You've seen it. When I delete 10K records on my previous test, I had about 500K wall. When I delete 10K from the partition table, I'm effectively deleting records. Although they're in one partition, I generate this the same amount of wall. And when I remove one partition, just my 10K records, by dropping the partition, I generate a lot less wall. In my previous demo, the numbers were different actually. The bonus question for the audience is, what happens if those partitions become gigabytes or multi-gigabytes in size? How quick and how efficient will my deletes be, and how efficient will dropping a partition be? You can take that one home as a homework. My main demo, my main point is made. I'm dropping a partition and I'm saving on the wall effort. So I do less writes, less streaming, less replica, all a lot less data to process out there. I'm saving time as well. And on large volumes, on significant databases, this thing really counts. Partitioning is a real efficiency enabler. Let's go back to the PowerPoint and look at the other advantages. I would normally look at the audience and ask any questions, but there is no audience in a pre-recorded part. That was the demo number 1. I hope the demo landed. The second advantage that I talked about is to make your queries more efficient on partitioning. Let's have a look. What we want to do is we want to scan less data. We want to process less blocks, have less I/O, use less cache, make our queries more efficient in general. Typical use case would be aggregates, queries over a few partitions. If you have to query the whole table, you're not getting the advantage because you have to visit all the partitions. But if you can query just one partition, that might be an advantage. This will not work if you start looping over all partitions. And this is one of the mistakes that you see with partitioning. People have partitioning in there, they do a query and they say, oh, nothing's changed. Well, that's because you're visiting all the partitions. Let me show you. I've got a table. My records are random spread across the table. That's why I've got my sum. I'm going to query an amount or do a count or a sum or an aggregate on some sort of range of data. In a normal table, this would probably mean a full scan. So I'm going to read through the whole table, I/O the whole table, examine all the records and decide whether they have to go to my sum or not. This is going to take time on a large table. Now I do that on partitions, and I might know where to look. So if my query knows where to look, then I don't have to scan the whole table, but I might just scan one partition. And that's where my advantage comes out. If you know your data, if you can control your SQL, you can get this advantage. Keep in mind, you need both. You need to know where your data is, so you need to know your partitioning scheme, and it has to fit your application, your business requirement, so to speak. And you have to control your SQL. You have to be able to point your SQL to that particular partition. And then you might end up scanning just one partition like this, and you do about a quart of the I/O, a quart of the effort. Demo time, conventional table, partition table. Do a select or a sum or a count over a range. Define your range carefully. Make sure you're in a partition. And then the demo might just work. I need to reinitialize my partitions, by the way. So I'm recreating my partition table, put 40K records in all of them. And there you go. And there we go. Let's do a sum. So here's the idea. We aggregate data from a conventional table and a partition table. Ideally, that data is in one partition. Let's have a look. So I'm selecting a range, I do a count, I do a sum of the amount, out comes a record. The total number of records counted was 10,000, and the aggregate of the amount data is about 495,000 as well. We looked at 10K records from a table of 40K. So this was the conventional table. Explain plan, let's have a look. Explaining the same query, I'm doing a sequential scan on that table, and it cost me about 6,000 cost number, whatever it is. It doesn't quite correspond to IO blocks, I know. So the optimizer decided to scan that table, and the cost is in the order of 6,000. That was the conventional table. I'm doing the same thing now for partitions. So I've got my partition table, same query, different table, same result, no surprise. We've counted the same number of records, we got the same amount of sum. The explain plan on this one is slightly different because I'm only scanning one of the partitions. See, luckily, all this data with this where clause is in partition number 2. So I can do a full scan of partition number 2, and I can ignore the rest of the table. That gives me a cost of about 1,400 or 2,400 after the aggregate. See, there's the cost is lower, and this is where your advantage is. We haven't even touched an index on this one. The best gain is always on full scanning of a table versus the full scan of just a single partition. And the whole demo is, of course, rigged to point that out. And the point is, if you can eliminate your partitions, if you can run your query on just one partition instead of all the partitions, you get a lot faster result. And on large volumes, of course, this is going to count. So that was demo number 2. We demonstrated that queries can be a lot faster if you can limit them to certain partitions. There is more. Of course, a lot of your queries are to find specific records. You're looking for something. If you're looking for the key field, you need to find one record. You know the key. That's easy. There is the local index or the primary key index, which is a local index, and you point to the record straight away. But if you're looking for all the fields where a property is yes, an active is yes, you can find multiple records all over the table. You don't know if those records are in one partition or not. You want an index on the field called active, but that index is going to be local. How many partitions do you need to scan to do that? And would you consider having a global index? You know, I know there's discussion about getting global indexes in Postgres. Let's have a look. The anti-pattern that you'll run into is if you have to loop over, if you have to visit all the partitions, all of a sudden your partitioning system becomes less efficient than a complete table scan. Let's have a look. Suppose you have a conventional table, you've got your records, you've got your index. If you look for an ID field, a key field, that's a primary key lookup, that's easy. The primary key is in the index, you jump through the index and into the table. You probably have to do 1, 2, 3, 4 blocks of IO. Now you're looking for a property called active. So active is yes, we have an index on that property. So all the N fields are in the index, and there's a few yes fields at the end of the index. The range scan goes to the bottom of the index, find all the yes items, and point to them. And there you have them. This would be 1, 2, 3, 4, 5, 6, 7, probably 7 IOs in a system, in an ideal system. This is a global. This is what a global index on a normal table, conventional index on a conventional table will do for you. Now, what happens on a partition table? Here's your partition table, 4 partitions, 4 local indexes. Looking for ID 1 is easy. You go to the index where you know that you go to the first index on the first partition. You know it's in there because ID 1 is in the range for that partition. You find the data with 1, 2, 3, 4 hops, possibly. You know you don't have to look at the other partitions because there cannot be an ID 1 in those other partitions. That's easy. So Postgres, your database, knows where that data is, and it only has to visit one index and one partition. Now, what happens if you look for something called active is yes, or a property, or a name, or whatever, and that's not part of the partition key? Every partition has their own local index with all the n's, and a single yes field for that partition are in this index. The second partition has its local index with all the n's and a few yes in that index, and the third partition and the fourth partition. So I'm looking for active is yes. I visit my first index partition. I do my jumps 1, 2, 3, 4. I find my record, and it could be more than one. But I have to visit all of those local indexes to see if there is a yes in there, and if there is, I have to find it. I have to visit 4 partitions, and I'm doing about, if you count it up, you end up with about 12 hops or 12 IOs. If you have 7 years of archive with 365 partitions per year, you end up with a lot of loops. You have to do a lot of hops, and all of a sudden you start to do much more IO than what you would do on a normal conventional table. This is your anti-pattern. This is what you have to prevent if you want your queries to remain fast, really. So let's have a demo on that. We get conventional table, partition table. We look for something called active, and we do that using the index. We already know there's only 4 fields, by the way. So let's do that. I've got my local index, and I'm going to pinpoint a small range of records. I'm creating an index on a field called active on my partition table, and I'm creating the same index on my conventional table. I analyze them for good measure for the cost-based optimizer. So we have indexes on those fields now. Let's select. We select all the fields where the active property is yes from the conventional table. We end up with 4 records because I put 4 records in there. And let's check if we've used the index. Lo and behold, we explain the query. We see that we did an index scan on the recently created index. The cost is 8 something, and there is your query. This is an efficient lookup of those records. That's fine. Let's do the partition table. We select the same fields from partition table. Where active is yes, we get 4 records again. But we happen to know they're from 4 different partitions. So what does the explain plan look? Well, there you go. You've got a scan of the index of PT1, a scan of the index on PT2, a scan of the index on PT3, and 4. We got cost and cost and cost and cost. We end up with 4 times the cost, actually. The total cost is 33 instead of 8 on the previous query. So this is the main point. Those indexes can lead you to a lot of looping. And people will raise their hand and say, yeah, but this is why we want global indexes. The global index might be much more efficient here. Well, Postgres doesn't have it yet. And I would argue that you're maybe even lucky not to have global indexes. But if you want to avoid looping over all your partitions, your SQL has to know in which partition it has to look. Your SQL has to limit itself to 1 or few partitions. That means that all your application code, every query in your application has to know which partition or partition limit it has to go to. On large volumes, this is going to count because your looping will become really expensive if you have thousands of partitions. But you have to put in the design of your queries where your partitions are. You know, this is my main message. If you use partitioning, you have to put it in there from the design stage on. And here's your global index. There's trouble ahead, actually, because if you do get those global indexes, people will create indexes on partition tables and they'll start looping. Your most partition databases that I've seen have failed because of global indexes. This is actually the background of the talk. This talk is here to warn you about the problems of partitioning. The old joke is a fail is nothing but a first attempt in learning. And a number of DBAs and designers, developers have learned that partitioning is not the solution. I've seen maybe 15 partition systems. 2 of those were a good success, perfect. The others were more or less a failure. Some of them were saved by the hardware because you can get hardware to fix any problem, mostly. Now, partitioning is often by date or time. That is the most logical thing to partition on. But your primary key is often an integer, a character field, or a GUID. And your primary key has to be unique. You need a unique index on that. To enforce uniqueness, you need that index. And if that becomes a global index, here's you run into trouble. You've got your partition table with your active fields in there. Your table is partitioned. Suppose you create a global index, a single index that can point to all the partitions at the same time. So this is allowed to point everywhere. It's not there yet in Postgres. You'll have it soon. So all the n's go in there and a few yes at the bottom. And the pointers are all over the place. The index points to all the partitions, and that's fine. Because I'm going to look for active is yes, so I can jump through my index as if it was an index on a normal table, and I can find 1, 2, 3, 4 records in there, and I've got about 7 jumps to go. And this is efficient, and I don't have to loop over all those local partitions this time. I want this, right? Right. It's potentially very effective, no looping. But this is what happens on a drop partition. Here's my first partition, and I've decided I don't need number 1 anymore. I can drop it. I've got my pointers from the global index going everywhere, and several pointers, several index entries point to partition number 1. Let's drop it. So there it goes. Poof, it's gone. You can see the problem because these pointers point to nowhere anymore, and these pointers point to nowhere anymore, and effectively that whole index data needs to be reworked. You need to rebuild that index, and this rebuilding an index means you have to rewrite the data for the index. You'll generate vol. You'd have to wait for the process to complete, and you're doing work either in the foreground or the background of your process. This is the challenge of a global index. The people who work on it already know this. The people who are enthusiastically waiting for partitioning and global indexes, please beware of this. There is a trick you can, and this is what we came up with in a couple of places, and it works more or less. There's at least one trick to get around that, and I'm not saying it's a good idea. Your mileage may vary, but this is one of the tricks. Because partitions are mostly a date thing. There are, of course, other partitionings like list partitioning on customer ID also happens. It's effectively sharding. I'd like to discuss that sometime. But you do not, suppose you really don't want global indexing. You've seen the presentation and you went home and said, we can't have global indexing. And you can only have one unique key then. Your unique key has to be the partition key, has to be the primary key. So how are you going to fix that if you want to partition on date? Did I mention design? So you have to think about this before you put the whole thing into practice. Here's what you can do. You can take a big int and decide that you want the integer to be a 2-part thing. The integer is going to contain a date and a sequence. The date is going to be something like year, day, and second. 300 days in a year, 80,000 seconds in a day. You need 5 here. And then you put another set of digits behind it. You put the date in there, and you put the sequence, and you tell the sequence to cycle at 9, at 1 million. So the sequence never goes over 1 million. You end up with something. You could use the epoch, which is a 10-digit sequence of seconds, and then add your sequence to that. You end up with 16 digits. You could use year, day, and seconds. You end up with 18 digits if you do that. You could use year, month, day, and 24 hours and minutes and seconds. You'd end up with 20 digits if you do it this way. The first one, an epoch, is not really readable by users or developers. The second one, where you put the year, the day, and the seconds together, is more or less readable. by developers. And the third one is the most readable ones, but it also takes the most digits. You need 20 digits if you want to do that. You could check, there's a good blog by Frank Pachot on primary keys and GUIDs, by the way. If you consider doing this with a GUID, maybe don't. GUIDs as a primary key are fine, but maybe not in a serious database. I'm a bit skeptical about using GUIDs for primary keys. So if you do this with your two-part key, your 64-bit integer, you end up with something that is 18 digits or 10 bytes in size. And you can suddenly do range partitioning. For example, on the first part of that integer, you can do range partitioning on 5 digits, the first 5 digits of the integer. And suddenly you have your partitions. You know that in a certain partition is all the data from today, 2020. We are in about the 320th day of the year. And if you use EDB EPAS, you can even have those partitions created automatically. You can tell, and this is the difficult part, you need to tell all your queries to limit themselves to a small number of days so that your ID is always bigger than the first part of this integer. You'd have to do something like generate the number based on today's date minus X number of days. That way you always query a limited set of partitions and your queries remain efficient. I know this is a far-fetched one. I know this is definitely not best practice, but we should discuss maybe. Now I come to the summary of my talk. The easy part, you ask the customer for their watch and you tell them the time. Partitioning only works if you put it in the design right from the start. Partitioning will give you less write-ahead log, less vol data. It'll make your whole system more efficient if your drops, your attach and your detached are suitable in the partitions. Partitioning can make your queries faster, but only if you can limit your queries to the partition keys. So every query needs to know to which partition it has to go. This is a design thing. The useful cases for partitioning are things like time series, audit data, data coming in with an important time dimension, any fast-moving data where data comes in and gets to be deleted after 3 months or a year or 7 years, suitable for partitioning. If you want to consider sharding, you could think about list partitioning. This is something I'd like to discuss with people who build serious large databases. I am of the opinion that list partitioning is just another form of sharding, but we can discuss. The main message is you have to know your data, know your system, and you have to control the queries that go into the application. Basically, you have to know your system. Otherwise, don't even start with partitioning. It has to be in the design phase, and then it'll work. What you should try to avoid, tell your developers not to do this. Maybe avoid global indexes. Like I said, of all the Oracle systems I've seen with partitioning, the mistakes were almost always, or actually uniquely, global indexes. Any global index will break your partitioning system. What you also have to avoid is looping over partitions, because as the number of partitions increases, you end up with 1,000 partitions. You suddenly get a query that used to be really quick, has to loop over 1,000 partitions after 3 years. It becomes really slow. You don't want that. As a consequence, the queries need to know the partition key. And as a consequence, it has to be designed from the start. Bolting on partition on an existing system is almost a no-no. We have interesting times ahead because you'll get your global indexes, and I'm curious to see how that will land in the Postgres community. And there are features like list partitioning or dividing data over storage tiers. You can do that with partitioning, and it's great for that actually, but it takes a lot of work. You'll end up putting data in table spaces on disk systems that you can compress, and that's a good feature. Partitioning can help you do this, but in my opinion, that is advanced partitioning. First, you have to get your partitioning to work properly. So we should discuss, what do we do next year? What do we want to talk about next year, maybe? Don't take my word, read the manual. And the Postgres manual, by the way, is a really readable thing. Play with it yourself and test it. If you want to discuss partitioning, there's a guy called Herman Beer at another vendor who is the partitioning tsar of that system. And he has interesting views. He's open for discussion, by the way. You can contact him via Twitter or find his email. Whatever you design, keep it simple. If it's not simple, if you can't explain it to me, it's probably not a good idea. And you'd have to explain it to the next person. You have to explain it to your successor. Anything really complicated you design, you build, you maintain, you end up in trouble when you hand it over to the next person. I have a blog. You can reach me on Twitter. Those of you who want the demos, they're on GitHub, but you'd have to ask me for the location first. This is my favorite German poet. Again, what he said was, if the real master only identifies himself with simplicity, simplicity shows the master, is the sentence. That's it. Normally, I would look at the audience and ask for questions, and I out there ask to see if anyone's left the room already disgusted by my opinions, maybe hear what you guys done. You can shoot at me. If there is time left, the only thing you'd have to remember, thank you for listening. Thank you for hearing me out, looking at my demos. And if there is one message, if you can't explain it simply, you probably don't understand it. This is always my final one.